Good morning, students. So, day 9 today, and what we are going to do today? Fluid mechanics. Very big chapter, but weightage in NEET is very less. Considering how much big it is, weightage is less. Okay, but no issues. So, let's start. Fluid mechanics. Okay, so what are we going to study in this? Density. You all know what density is. Okay, how much volume is occupied by a unit mass? Mass occupied per unit volume. Okay, mass of a unit volume. Mass per unit volume. Density is mass by volume. Unit kg per meter cube, or in CGS grams per cc, centimeter cubic or cc. Okay, 1 kg per meter cube equal to how many gram per cc? Very important. 1000 gram per cc. Let's see, am I correct or not? Because conversion units and dimensions we have studied that. So 1 kg means 1000 gram, and 1 meter cube means 1 meter means 100 cc. So 100 cc cube. So 1000 gram by 10 to the power 6. So actually 10 to the power minus 3 gram per cc. Not 1000. Okay, check. Have I done correct or not? Let's check it first. 1 kg per meter cube. 1 kg is equal to 1000 gram. 1 meter equal to 1000 centimeters. So not cc, centimeter. Right. So now 10 to the power 6 cc, centimeter cubic. So what we got? 10 to the power minus 3 gram per cc. Okay. Density of water is what? Density of water is either 1000 kg per meter cube, you write, or 1 gram per cc, you write. Both are same. Okay. 1000 kg per meter cube will be given, or 1 gram per cc will be given. That is the density of water. Okay, fine. Then we have relative density. Relative density is ratio. Okay, what ratio? Density of a substance to density of water. Density of water at 4 degrees centigrade. Right, this is relative density. So what we do with this, in certain questions they will give you relative density and you have to find density of a substance, whereas this is known to us, 1 gram per cc or 1000 kg per meter cube. Okay, so with that you can find density of a substance. Right, relative density is units, unitless, because density by density, dimensionless. Okay, so density of substance by density of water. Okay, it's a dimensionless and unitless quantity. Fine. Then what we have? Then we have pressure. Pressure. So when you apply the force at any point, what do you create? You create pressure. Okay, when we are applying force on any object, we create pressure. And what pressure is? Force per unit area. Force applied per unit area creates pressure. And this is force per unit area. P equal to F by A. Okay, so if I am going to take one area which is like this, Okay, and on this one, we are applying force. This is area. Okay, so pressure is F by A, no doubt about that. But if suppose on same area, force is inclined. Okay, force is like this. It's inclined. Value is F only. Now what? So now first thing is that we have to find what is the angle. Suppose this is the angle, this is theta. Okay, with the vertical, this is making an angle theta. Now what is the pressure? So now first of all we will see what are the components. This component is F cos theta and this component is F sin theta. Now what is the pressure? Pressure is F cos theta by A. That means if we want pressure to be created, force needs to be perpendicular to area, then only pressure will be created, otherwise it is not created. And F sin theta anyhow is not applying pressure. It's a tangential force. It cannot create pressure, only perpendicular force can. So remember always this pressure actually we used to write as F perpendicular to area, F normal to area. Okay, unit Newton per meter square or Pascal. Newton per meter square or Pascal. Scalar or vector? Scalar. If scalar or vector only are the options, scalar. Okay. Then units, force unit, not units, dimensions. Force dimensions are m, l, t minus 2 and area dimensions L square. So what we are getting? M, L minus 1, t minus 2. Okay. M, L minus 1, t minus 2. That's pressure. Okay. Then what next we have? Next we are going to see Pascal's law. But before that we know atmospheric pressure, right? What is atmospheric pressure? 1 atm. 1 atm. It is 1.013 into 10 to the power 5 Pascal. Okay, this is measured with barometer, and what we measure through barometer, it is equal to 760 mm of mercury or 76 centimeter of mercury. What this is actually, what is 76 centimeter of mercury? Actually, this much weight of mercury creates this pressure. We will see that. So at the moment, atmospheric pressure is 760 mm of mercury or 76 centimeter of mercury. Okay, created by mercury column. Right. Then what next was? Pascal's law. What says Pascal's law then? Very important law. Pascal's law says that if there is a liquid in any container, if at any point we are going to exert pressure, same pressure is transmitted throughout the liquid. If at any point we are going to exert a pressure, that pressure will be exerted throughout the liquid. Same pressure, undiminishedly. If suppose 5 Pascal you are exerting at one point, so at other end also 5 Pascal is going to be the pressure, an extra pressure. Okay. If pressure is exerted at one point of liquid, same pressure is transferred throughout the liquid. Okay, Pascal's laws usage are huge usage, and when numericals that we are going to do in almost 80% of the questions, we use this. Okay, But practically what uses are there? We know that in elevator, hydraulic elevator is the first one. And on this one, you can find question also in the books as well as in NEET. Hydraulic elevator, and second one we'll see brakes. Hydraulic brakes. These brakes we use in cars, right? So hydraulic elevator, very common thing. What it is? So there is a device, not device actually, a process that is performed. Something like this. Okay. Here this is piston, here this is piston. Okay, this area is very small, it is kept very small, and inside this one is what? Liquid is there. So we can fill this with a liquid if we want. Okay, like this liquid we can fill. Right. Same liquid throughout. Like this it is. Okay. So now its area is kept very less here. Maybe like A is equal to 0.1 centimeter square you can keep. And here area is kept big, only like 10 centimeters square. Okay, and suppose we are going to apply a force of 5 Newton. So when you apply a force of 5 Newton means how much pressure are we creating? 5 by 0.1 centimeter square. Let it be in centimeter square only, no problem. Okay. So what will be our unit? Newton per centimeter square. Okay. So pressure that we have created is 15 Newton per centimeter square. Now same pressure will be transferred throughout. So here also same pressure will be there. And how it will be exerted? Like this. Like this will be the force. Okay. So how much is this force here? That we have to see. So here again pressure equal to F dash or F1 by area 1. So what is that? Pressure is this 50. F1 by what? 10. So you see that the force that we are getting is 500 Newton. 500 Newton we got. What we applied is 5. What we got is 500. Okay. So suppose that I am going to decrease its area or I am going to increase its area to 100 centimeters square. So what will happen? I will be getting 5000 Newton. So with the help of this, here if we are going to keep the car, that car can be lifted easily. Car can be lifted very easily. 50 kg, 500 Newton is 50 kg. 50 kg you have lifted just by applying 5 Newton. Correct? If you apply 50 Newton over here, then what will happen? So you can lift very easily over here. So what we have to do in this one, we have to equate pressure that you are applying here and pressure you are applying over here. And then they can ask you, either they can ask you the force, they can ask you the area, depending on the question. Okay. This is hydraulic lift. Second, hydraulic brake. Now hydraulic brake we all have seen. Okay. Because we have all traveled in car. When car moves with very high speed, it has very high kinetic energy. And if you suddenly want to stop it, okay, what we do? We apply brake. And we all know that car cannot be stopped by 4 or 5 people. If we are making them to stand in front of the car and tell them to apply the force, you can't stop the car. But a little push of the brakes can stop it. And that's where the Pascal's law is very handy. So what we do, if I make the diagram, you will try and understand that, okay. So how it is? Something like this, okay. And here is this piston, okay. Here is this piston where this brake paddle is there. Okay, so through this brake pedal, you are applying the pressure. You see that small area is there, very, very small area here. And here what? Here that liquid is there, that oil. Okay, oil is filled. So here that oil is there. Okay, and then there is opening here. Then you can have something like this. Okay, then this is a diaphragm or something like spring. Okay, and here are shoe brakes, and here is this wheel of yours. This is wheel. Okay, then I think one mistake I have done in the diagram. Right. No. Okay. All right. Something like this. Okay. So this liquid is also here. Here. Okay. So when you are applying this pressure, that pressure is coming from here. Same pressure goes here. So when the same pressure goes over here, this liquid, whose pressure is increased because of this Pascal's law, okay, starts applying pressure on this diaphragm. Okay, all sides. What will happen to this diaphragm? It will expand. When it will expand, it will touch the wheel. And on this diaphragm only, there are brakes. This is brakes. Okay, these are brakes. That will come in contact with the wheel, which is rotating. So when they will come in contact, they'll be pressed against the wheel. What will happen? Wheel will stop. This is how hydraulic brakes work. Small push over here will make a huge pressure over, because here area is huge. Here area is very small. Okay, but here area we have made very big area, and because of that what happens? This is pressed against the wheel and wheel stops. So this is how hydraulic brakes are working. Okay, this is Pascal's law. Now what next we are going to study? Going to talk about gauge pressure or gauge pressure. What is gauge pressure? Extra pressure other than atmospheric pressure. If suppose at any point we are measuring the pressure, it comes out to be more than atmospheric pressure, then how much pressure is more than atmospheric is called gauge pressure. Okay, how much pressure is more than atmospheric pressure is called gauge pressure. At any point, suppose whatever pressure you are having, it's called absolute pressure of that point. And absolute pressure of that point is equal to pressure atmospheric plus gauge pressure. So what is gauge pressure then? Gauge pressure is absolute pressure minus atmospheric pressure. So it means at any point you have pressure as 3 atmospheric. Then what is gauge pressure? 2 atmospheric. Okay, what is gauge pressure? 2 atmospheric. Gauge pressure is always absolute pressure at any point minus atmospheric pressure at that point. Okay, how to measure it? Okay, so how pressure varies with the depth, that we are going to see now. Let's see, here only we will be seeing that. Suppose we make one container here. Take a container. This is container. Okay, and this is filled with liquid of density rho. So we'll fill it first. So it is filled. Okay, right. This is up to high dash, it is filled. Density of liquid is rho. So I want to know the pressure at any point, maybe at the base. Pressure at the base. So now the question is, who's applying the force, because pressure is force by area. So it is the weight of this liquid. Who's applying? Weight of this liquid is applying the force on this one. How much is the weight? First of all, I say pressure. Pressure at the base. You say weight of liquid by area of the container. Weight of the liquid means mg by area. Okay, how much is weight? Volume into density into g by area. What is volume? If base area I am going to take as A, suppose base is circular base A. So we can say volume is A into H into rho into G by area A. So what is it? Rho GH. Pressure here is rho GH. Okay, now you can see that this is open to atmosphere. So atmospheric pressure is being exerted. If it is open to atmosphere, atmospheric pressure is here. So if you apply Pascal's law, we say that here atmospheric pressure is getting exerted, then same pressure is going to be transferred throughout. At every point this will be transferred. So here also P naught will be there like this. So obviously same has to be transferred. So what is total pressure at the base? P naught plus due to weight of liquid. So total pressure at base, that absolute pressure at base is what? P naught plus rho GH. So what is gauge pressure? Rho GH. Okay. Gauge pressure is rho GH. This pressure increases as you go down. In a river, yes. In a sea, yes. It increases. Okay. So this is due to weight of liquid, and if it is open, if it was not open, then this is our answer. Okay. If container is closed. This is the pressure. And if container is open, this is the pressure at the bottom, and this is gauge pressure. Okay. So this is how we measure pressure at any point. Okay. Then based on this only some questions are there. Questions are, if container is like this and another container is same way, straight only. Okay. Like this only. And another one we will make something like this. Something like this it is. Okay, in all of them, the liquid which is there, which is kept at same height, in all of them. Okay, so liquid is having same height, and their area also, base area of all is same base area. Okay, here also this is A. This is also same A. Okay. Density is same. Now we all know that the weight of liquid in all of them is different. Weight is different, but pressure at the bottom in all three cases is same. Pressure at bottom in all three containers is, if suppose atmospheric pressure is there at the top, then we'll write P naught plus rho GH, otherwise rho GH on. Even though weight of the liquid is different in all of them. Okay, this is called pressure paradox. Why this is? Now, where is weight of liquid maximum? You say here, because it's open. Okay, it can accommodate more liquid. So, in this one, what happens? In this one, why pressure here and pressure here is becoming same? The reason is that extra liquid. How much is extra liquid? This is extra liquid, right? If we compare this with this one, where is extra? This is extra. So its extra weight is balanced by this normal contact force because it's inclined. Here normal contact force is. This normal contact force balances the weight of extra liquid. Here there is no problem. Entire weight is acting down. In this one weight is less. Okay, so in this one what happens? This container's wall are applying normal contact force like this. Okay, they are applying normal contact force in this way. This is N and this is N. Okay, so because of this N, they are compensating the weight of this liquid, which could have been, if you are comparing it with this one, this much liquid is less. So these normal contact force are balancing it. So certain times they ask you that what is the normal contact force exerted by walls of the container. So what you will do? What is normal contact force? Normal contact force is the difference between weight of the liquid and force exerted due to pressure at the base. Okay, I am writing it. Normal contact force is what basically the difference. Okay, now why I am putting in mod? Because in this case, if you see, weight is more. In this case, you see pressure at the bottom or the force due to pressure will be more. Okay, so what it is here? N equal to what? Weight of liquid minus pressure at base into area. That only is the force, right? In this case, what is there? Pressure at base into area minus mg. In this case, 0. Normal contact force is 0. So, if they ask you what is the normal contact force exerted by walls of the container, these are the anything. This also you remember because I have already put in mod. So, you will be getting the same answer. But you have to remember that in this case, normal contact force acting down. In this case, it is acting up. Okay. These are regular shapes I gave you. If suppose that some shape is given like this, then like this. And this one, water is there up to height h or liquid is there up to height h. Then what will be pressure at the bottom? Same, rho gh. Because pressure doesn't depend on area. Okay, so don't think that area is very less as compared to this one. It doesn't depend on area. Where is area here? Okay, so pressure will be same rho gh. Which pressure? Gauge pressure. Gauge pressure will be rho gh. Okay, this is pressure paradox. On this one, we are not doing any question at the moment. Okay, right now we are moving on to barometer. What is barometer? A device used to measure atmospheric pressure. Used to measure atmospheric pressure. What is this device? Open container. Okay, contains mercury. So mercury is here. Then what we do? We bring one inverted tube in which vacuum is there. Something like this. So in this one, what happens? Mercury goes up. Why it goes up? Because in this one, vacuum is there, zero pressure. Here, atmospheric pressure is there. So liquid moves from higher pressure to low pressure. It went up. Now it went up here, up to height h. Okay, up to height h. Okay, what happened? Right, then it stops. Now it's not going further up. So what happens now? Now when it is at rest, then remember that at the same level when liquid is at rest, when liquid is at rest, at same level, in same liquid, pressure is same. At same level in same liquid, pressure is same. So that means pressure here and pressure here is same. Now here pressure we already know is P naught. What is pressure here? Here we are saying already P naught, 0 pressure, not P naught, P equal to 0 here. Now this is height. So we know that pressure here will be, whatever pressure is here, that is 0 plus rho gh, because of the depth of the liquid, because of the weight of the liquid here. How much is pressure? Rho gh. But here pressure is P naught, and we are saying at the same level and same liquid pressure is same. So that means P naught actually is rho gh. Now from here, that 76 centimeter of mercury column, this is called 76 centimeter of mercury column equal to 1 atmospheric pressure. If you are taking mercury, it will go up to what height? 76 centimeter. That's how it comes. This is atmospheric pressure. Okay, right. Then another device is there, manometer. Manometer. Manometer is U tube, something like this. Okay, now what it is used for? It is used to find the pressure of any gas or liquid. Right. In this one, what happens actually? Initially, mercury will be there, and mercury will be in the same level. Why same level? Because on both sides, it is open to atmosphere here. So here also atmospheric pressure, here also atmospheric pressure. So it will be in equilibrium. So level is same. Correct. Now, if suppose that you want to measure the pressure of something, some gas or liquid, suppose gas. So what will happen is we are going to connect it with some gas chamber. Suppose like this. So from here, what will happen on gas? Okay, gas will go. Okay. Now this gas is going to exert pressure on this mercury. It will go down. Okay. So here this gas is there. Suppose mercury comes down up to this. Then what will happen on other side? Other side mercury will go up. This will happen. Right. Now it's at rest again. It's in equilibrium now. So now what do you say? You have to find pressure. So here at this point you have a pressure of gas. Okay. So now we have studied that at same level and same liquid pressure is same. So this is your mercury. So you will say that okay, this level we are going to see. Okay, here is mercury, here is also mercury. Then we will see that how much height up it has gone. Okay, so pressure here and pressure here will be same. Here what is there? Here at P naught is there. So we will say okay, pressure of the gas is equal to pressure here. What is pressure here? P naught plus rho gh. This is how what is that? Manometer works. Okay, we can find pressure of the gas very easily with the help of manometer. Okay, now let's do a few questions. Okay, on barometer as well as manometer. So question says, if a barometer that gives reading of 76 centimeter for atmospheric pressure, is kept in an elevator moving upwards with an acceleration, what will be reading of barometer? What will be reading of barometer? Okay, options are given. 76 centimeter, greater than 76 centimeter, less than 76 centimeter. Okay, D is 0 or none. Okay, this is a question. Now, how to do this? What is happening? He is talking about elevator. Okay, so we are in elevator, and once we go in elevator, what happens to atmospheric pressure? Does it change? Answer is no. It remains same. Okay, elevator. We are not talking about that we are going 50 kilometers, 15 kilometers above the sea level, or 10 kilometers or 5 kilometers above. We are not saying. Just going in elevator, and elevator is going to maybe second floor, third floor, or maybe 10th floor also. Okay. So we have atmospheric pressure only. Then what happens? We saw that in barometer, it is normally P naught equal to rho g h. Okay, what happens now when this elevator goes up? The effective value of G is not G, it becomes G plus A because of pseudo force. Okay, if the elevator is going upwards, okay, then what happens? What happens to any mass? Normally it was mg only, but now what is acting? This is normal contact force. Or you can write n minus mg equal to ma. Even then there is no problem. In that case also this will come same. Here I am writing n is mg plus a. But if you don't want to take pseudo force, then what you will write? N minus mg equal to ma. Then also n is same. See what I have written. So n value is increased. That means g value has increased. Effective value of g, not g has increased. Effective value of g is g plus a. So here I am going to write now. This is P naught only. Rho g plus a into h1. Correct or not? So what will be h1? More than h, less than h? Less than h. See. Rho gets cancelled. h1 is what? G by g plus a into h. So obviously here denominator is more than g. So h1 value will be less than h. So that means less than 76 centimeter. Less than 76 centimeter will be our answer. Okay. Alright. Next is a simple question. Okay. Find the gauge pressure at 20 meter depth in a lake. Okay, gauge pressure only is asking. Find the gauge pressure. Don't write P naught plus rho gh. Only rho gh he is asking. Sometimes we do that kind of a mistake also in exam. Okay, so only gauge pressure. Okay. P gauge is rho gh. Now water is given, so directly I am taking its density as 1000 kg per meter cube, G is 10 and this is given 20. Direct, finished. 1, 2, 3, 4, 5. Our answer is 2 into 10 to the power 5 Pascal. Absolute pressure if he is asking, add atmospheric pressure 1 into 10 to the power 5. It will become 3 into 10 to the power 5. So gauge pressure here is rho GH. Okay. Alright. Then let's frame one question. Say pressure at 10-meter depth of lake is 2/3 of pressure at bottom. Pressure at bottom. Find depth of lake. Okay, pressure at 10 meter is 2/3 of pressure at bottom. What is depth of lake? And we are talking about water only, so that's why I am not giving you density. Okay. The solution is pressure at depth, 10-meter depth. Okay, which pressure? Gauge pressure. Okay, 2/3. Fine. What will do? Pressure at 10 meter is equal to 2/3 pressure at bottom. So if I am going to say that the depth of the lake is h, so we will be writing this as 2/3 rho gh. Okay, is equal to what? Pressure at 10 meter. So pressure at 10 meter, what? Rho g into 10, we will write what else? So that's it. Over. 30/2, h is equal to 15 meter. That's it. Over. So this way we can find out that what is the depth of the lake very easily with the given data. Right? Okay. Then let's see what next we have. What more we can do? Okay. Another question says there is a bubble at the bottom of a lake. Okay. When it comes up, its radius doubles. Okay. When a large bubble at the base of lake comes to surface, its radius doubles. Okay, its radius doubles. Then find depth of the lake. Find depth of lake. Actually, this is combination of fluids and thermodynamics actually. Okay, so what's happening in this one? When this bubble, inside bubble is what is there? Air is there. Air bubble will be there. So we are talking about gas as such, right? So we say that when this bubble is going to move from bottom to the surface, temperature doesn't change. Temperature of water remains same. So temperature of the gas inside also remains same. So it's an isothermal process. So when it's an isothermal process, we are saying, then we can say P1 V1 equal to P2 V2. Isothermal process, that means P1 V1 equal to P2 V2. Okay, so P1 V1 at the bottom first. So he says that at bottom, if I assume that its radius is r, and at the top its radius become 2r, right? So P naught, what are you saying? Rho gh. H I am seeing as the depth of the lake, okay, into 4/3 pi r cube. Now at the top, what is the pressure? P naught, right? P naught. Now this one, P naught here into 4/3 pi 2r whole cube. Correct or not? Clear? Or you can say, if in terms of pressure itself I say, suppose rho GH if I am not taking, if I say this is P and this is P1, okay, this is P1 or this is P1 or P2, okay, P1 and P2, okay. Now what we have? 4 by 3 pi R cube, 4 by 3 pi and R cube cancel. So what we have? P1 equal to actually 8 P2. Okay, so what we have to do? This has become 8 times. Pressure has become 8 times. When it goes to top, at the top, whatever pressure is there, it is 1/8 of the pressure at the bottom. P2 is actually P1 by 8. Okay, now what about gauge pressure then? Gauge pressure will be obviously P2 minus P1 or rather P1 minus P2. Okay, so gauge pressure will be P1 minus P2. P1 is P1 only or P1 is 8 P2, that we will say. Okay, 8 P2 minus P2. So what it is? 7 P2. And P2 is what? Atmospheric pressure. P2 is atmospheric pressure, right? Rho GH we can write. But what is the atmospheric pressure corresponding height in terms of water? We know it is 76 centimeter for mercury, but for water how much it is? Can we find it? Yes, that also we can find. See, how can we find that? Okay, so atmospheric pressure is equal to 76 centimeter of mercury. So 76 centimeter of mercury into density of mercury into G equal to height in water we don't know, density of water is 1 into G. G and G gets cancelled. So height in water is 76 into 13.6. 76 into 13.6. This will give you height. How much height will be there for water? Okay. Or in another way, slightly better way, this entire thing, atmospheric pressure we know is 1 into 10 to the power 5 Newton per meter square approximately. That's equal to how much height of water? Density of water is 1000. G will take as 10 into H. So 1, 2, 3, 4. So approximately height comes out to be 10 meter. 10 meter. So this is what 7 P2, that means 7 atmospheric pressure. Correct. So what will be the height? 7 rho G H. Okay. This is equal to pressure at the bottom or rather gauge pressure at the bottom. Rho G will cancel. It will become 7H and H is what? H is actually 10 meters. So approximately 70 meters. Okay. So height will come as 70 meters. Where pressure will be 8 times the atmospheric pressure. Okay. Right. What next? What next we can do? Manometer will solve few questions now. Okay. So manometer, what questions are there? So here is manometer. Okay, YouTube manometer, and as always initially there is mercury in this at the same level. Okay, now what we are going to do on one side in this one, we are going to pour glycerin. Okay, so glycerin we are going to pour in this one. Glycerin. Okay. one side glycerin we are going to pour how much? 10 centimeter. Okay, 10 centimeter glycerin is filled in one side of manometer. Okay, 10 centimeter glycerin we are going to fill, and its density of glycerin is 1.3 gram per cc. Okay, so on one side we have put the glycerin, and on the other side we are going to put oil. Okay, and this side oil of density 0.8 gram per cc is filled so that upper level of glycerin and oil is not same. Filled such that, not so that, such that upper level of glycerin and oil is not same. Okay, now we can see that this is having higher density, this is having lower density. So what will happen? Glycerin is going to push the mercury more as compared to the oil. So what will happen is, first there will be inequality over here, inequality in the level of mercury, right? So suppose it's like this. The mercury is up to this one, here is mercury, this one. Okay, now this side we are putting glycerin. So here glycerin is there. This is glycerin. Okay, and this side is oil. This is what the question is asking us. Okay, and this is given so far. Okay, so oil on one side, glycerin on the other side. Then what we have to find? Find the length of oil column. How much is this? Okay, glycerin already given 10 centimeter. Right, so find D. Okay, what to do? Again, we know that now everything is at rest, everything is in equilibrium. So take a liquid so that we can say that at the same level, pressure will be same. Which liquid will take? Mercury, obviously. Here. Okay. So here, whatever is pressure here, same will be pressure here. So who is exerting pressure here? This glycerin. If I say here is P naught pressure, then here is also P naught. So pressure here, at this point you say P naught plus density of glycerin into G into 10 centimeter. Okay, now here pressure is exerted by oil, but here's mercury also. Mercury is also exerting pressure. So how much is this? We can say this is 10 minus D. This is 10, and here this and this level are same. If this is D, then this will be 10 minus D. So what is pressure here? Now see, pressure we are writing. Pressure here is P naught plus, okay, first because of oil. So density of oil into G into D plus density of mercury into G into 10 minus D. Now everything in CGS, let it be in CGS, there is no problem. Okay, now we are going to equate both, that's all. So P naught plus density of glycerin 1.3 G into 10 centimeter. Here P naught plus density of oil 0.8 into G into D plus density of mercury 13.6 into G into 10 minus D. P naught is cancelled. Okay, what is this? This is 13G. 10 we are multiplying is 13G. Or rather G we can cancel throughout. That is also possible. Okay, so G, here is also G and here is also G. G is cancelled. What do you have? 1.3 into 10, so that is 13. Here 0.8D. 13.6 into 10, 136 minus 13.6D. Okay, bring it over here. 136 minus 13, that is 123 minus 123, and here is 0.8D minus 13.6. How much it will be? 12.8. Minus 12.8. Okay, so answer is coming 123 by 12.8. That's the value of D in centimeter. Okay, slightly less than 10. Slightly less than 10 is. So that is the answer. This is how we can do questions on YouTube manometer. Okay. All right. Now let's move on to Archimedes principle. What is Archimedes principle? Archimedes principle says that if you are going to put an object in the liquid or fluid as such, okay, air is also a fluid. So in air also there will be buoyancy force or upthrust, but it is negligible. Okay, but it becomes significant if suppose that we are jumping from the aeroplane with the parachute. Okay, the parachute, because of parachute we will be coming downwards slowly. Reason is buoyancy force of air. Okay, because you increase your volume because of the parachute. Because of that, buoyancy force is increased, and we are coming slowly downwards. Otherwise, if you don't increase the volume, we don't increase the buoyancy force, we all know that we'll be falling with acceleration due to gravity, and our speed will be very fast. Okay. So Archimedes principle is of fluid. So if any object is there which we are going to immerse in a liquid or a fluid, there will be upthrust acting, and that upthrust value is equal to volume of the object inside the fluid into density of the fluid into G. Okay. So any object immersed in a fluid experience an upthrust force that is equal to volume of object inside fluid into density of fluid, or in place of this, that is equal to weight of liquid displaced, we'll write. Okay. Then weight of liquid displaced we'll be writing as into and all that. Any object immersed in a fluid experience an upthrust force that is equal to weight of liquid displaced or weight of fluid displaced. Weight of fluid displaced. Okay. So buoyancy force or upthrust is equal to weight of fluid displaced by object. Now, how much fluid it can displace? How much volume it can displace? Equal to its own volume. How much volume it requires? Okay, if you putting any object in the liquid, how much liquid it will displace? Equal to its own volume, because it has to make its own place. It wants to go inside. Okay, it will create its place. So how much place it will create? Equal to its own volume. More it doesn't require. So, volume of liquid displaced into density of liquid into G. That is only weight of liquid displaced. So, we say here volume of the object inside, volume immersed into density of liquid into G. That's only buoyancy force. Okay, and this is what told to us by Archimedes. He discovered it. It was there, not that he invented, no, it was there, it is a discovery. So, buoyancy force is volume of immersion into rho of liquid, this is rho, okay, not L, rho of liquid into G, okay, right. Then suppose there is a container, okay, there are three cases. All three cases are like if in a container you have an object like this. So, how much volume of this object is inside? Say 0. 0 volume is inside. So, what is buoyancy force on this? Buoyancy force is 0. Second case. Second case if we take, and we have third case also. Alright, we have to make separately only. Alright, this is third case. Okay, so in this one liquid is there. So in second case we have the object is inside, little bit inside. So in this one buoyancy force is 0? No, because it has created its space in the liquid. It has displaced the liquid. So if it has displaced, then there will be buoyancy force. So how much volume is inside? This much. Suppose this is X and this area is A. So buoyancy force will be what? Volume inside. How much is inside? AX into density of the liquid into G. That will be buoyancy force. Third case, fully inside. So fully inside is there now, object. It's here. In all three cases that we have made, all three cases, the object is floating only. It's not sinking. Okay. So here what? Here is entire volume is inside. So this time buoyancy force is what? Area into D into density of liquid into G. This is buoyancy force. Okay. This is also floating, this is also floating, this is also floating. Okay, fully submerged, partially, and not at all inside. Okay. Alright. So now questions are there on this one also. In floating case, what questions are there? It says that an ice cube, ice density is what? 900 or 0.9 gram per cc or 900 kg per meter cube. That means its density is less than water. Okay. An ice cube of side 10 centimeter is floating in water. Find how much volume of ice, how much volume of ice is outside water, how much volume of ice is outside water. Okay, density of ice is, as I said, 0.9 gram per cc and density of water 1 gram per cc. Okay, density of ice as well as water I have given you. Let's see, a minute now, just a minute. Right, students. So, will this ice be going fully inside? Answer is no, because its density is less. Okay, because its density is less, it will not go fully inside. Slightly it will be outside. That's what the question is asking us. So, if this is the ice cube, okay, then it will be like this. This is water. That blue is water. Okay, that blue color. So, how much is outside? That's what he is asking. This much is outside. How much volume of ice is outside water? Okay. So, how to find? It's a floating. Yes, it's floating. So, that means buoyancy force is acting on that. Okay. And if it is floating and it's not going down, that means its acceleration 0, net force is 0. Net force buoyancy is acting upwards, then who is acting down? Weight. So if it is floating, that means buoyancy force must be equal to the weight of the object, right? So for floating, buoyancy force must be equal to weight of object. Okay, so buoyancy force is what? Now we are saying that suppose this is x. Okay, total is 10. 10 meter, what is given? Not given. 10 centimeter given, right? So 10 minus x is inside. Okay, so how much total volume? Base area 10 into 10, and how much is inside? 10 minus x. So I am writing buoyancy force. See now, 10 square into 10 minus x. This much volume is inside. Into density of water. What is that? 1 into g. Must be equal to weight of object. Now weight is volume of the ice cube into density of ice cube into g. G and g cancelled. With 10 square, 10 square cancelled. So 10 minus x equal to 9. X equal to 1 centimeter. X equal to 1 centimeter. Only 1 centimeter is outside. But is he asking that? He is asking how much volume is outside. Okay. So volume outside. What is the area? 10 square. And how much is the side outside? 1 centimeter. 10 square into 1. So that means 100 centimeter cube is outside. Total volume is how much? 10 into 10 into 10. That means 1000 centimeter cubic. How much is outside? 100 centimeter cubic. Okay, so we got it. Ratio he wants 100 by 1000. 1 by 10 of a volume is outside. Percentage he wants 1 by 10 into 100. 10% is outside. Getting it? So this way they can ask the question from us. Alright. What more we can do? On Archimedes principle. Question is like this now. Suppose this container, we have one object. An object is like this. Okay. Now this object is in two liquids actually. One liquid is here, like this, and the upper liquid is something else, some other liquid. Okay, like this it is given to us. Right. Now what we can do, its density is rho, its density is rho 2, and its density is rho 1. rho 2 and rho 1 we have taken. So what we have to do is find fraction of, this is also, we'll take cube, it will be easy for us. Okay, this is a cube. So find fraction of cube in upper liquid. Find fraction of cube in upper liquid or find fraction of cube in lower liquid. Any question can be asked from us. Okay. And one information more, rho 2 is less than rho 1 is less than rho 2 is less than rho 1. Okay. What to do? Now in this type of a question, one thing is clear, because this object is displacing this liquid also and this liquid also. So buoyancy force will be because of both. So what will do? Is it floating? So yes, it's floating. It's not sinking, it's floating. So if it's floating, then weight will be balanced by the buoyancy force of both liquids. Okay. So weight is equal to buoyancy force by liquid 1 plus buoyancy force by liquid 2. What is weight? It's a cube. So let's say that its sides of length L will take. Okay. Okay. So L cube into density into G. That is the weight of the object. And that's equal to buoyancy force 1. That means this liquid here. So base area is L square. Now how much is inside? This will say this is X. Okay. So L square into X, this is volume inside, into density, how much? Rho 1 into G, plus buoyancy force on the second one, L square into L minus X. Okay. L square into L minus X into density into G. What we can cancel? G can cancel. L square we can cancel. L square, L square, L square. Now what we have? L into rho. Okay, this rho we have to write properly. Rho into L equal to X rho 1 plus L minus X rho 2. What we have to find? X value we have to find. Okay. So rho L equal to X rho 1 plus L rho 2 minus X rho 2. Okay. What we have now? That's it, right? So rho into L minus rho 2 into L equal to X, you can take common, that's rho 1 minus rho 2. Okay, L you can take common from here, L rho minus rho 2 by rho 1 minus rho 2. This is X. Now X is actually in lower liquid, but he is asking upper liquid actually. So actually we had to find L minus X. No problem, we can do that. L minus X we can find. So with that one we will find how much is inside. But fraction is asking again. How much fraction? That means L minus X by L he is asking. So L will get cancelled. Because total length is L, no? Then only fraction you will be getting. Or you can, if in terms of volume you want, then L square into L minus X by L cube. So both are same thing. Okay. So L minus X by L we will find, or if he is asking lower liquid, then we already found X by L is rho minus rho 2 by rho 1 minus. Okay. So this way we can find fraction also. What more we can do? What more type of questions can be asked? More type of questions can be, if suppose we have two liquids. Okay. This is liquid number 1. And in this one we keep one container. Okay, say half of the volume is inside here. Okay. Then we have another liquid. In another liquid, same object we are keeping inside. Okay. Same object. Same object. But this time it goes inside little more. Okay. 2V by 3. Okay, its density you can say rho. Density is rho. Okay. Then its density rho 1 and its density rho 2. Question is asked, what is relation between rho 1 and rho 2? Find relation between rho 1 and rho 2. Between rho 1 and rho 2. Okay, so here also it is balanced by buoyancy, here also it is balanced by buoyancy. Weight of, because it's the same object, it's the same object. Okay, so since it's the same object, what I can do, see, first thing is, let's do the weight equal to buoyancy force here. Okay, so weight I am writing is weight equal to buoyancy force is what? V by 2 rho 1 into G. Correct. Here, same weight equal to 2V by 3 rho 2 into G. Now, this is also weight, this is also weight, and the same on, equate it. So, V by 2 rho 1 G equal to 2V by 3 rho 2 G. G gone, V gone, and we got rho 1 and rho 2. That's what we wanted. So, rho 1 by rho 2 is what? 4 by 3. That's all over. Ratio of the densities of two liquids, 4 by 3. Okay. So, this is how Archimedes principle we do. One more thing is there in that one, sinking object. Okay. If the object is sinking, in that one there is a concept called apparent weight concept. Okay, apparent weight. Okay, fine. Object is sinking means what? When object sinks? When density of the object is more than density of liquid. Object sink in the liquid when density of object is more than density of liquid. Okay, in that one there is a concept called apparent weight. Apparent weight concept. And what is that? Apparent weight of object is weight of object minus buoyancy force. Minus buoyancy force. So if suppose that some ornament is there that you are going to put in water, we know that ornament will be sinking inside. So then buoyancy force will be acting, but still it will sink. So when you are going to lift it inside water, it will be lighter to you. It will become very light because you are going to have apparent weight. Sometimes when heavy load you have to carry, it is very tough to carry normally. If suppose that you are thinking that okay, we'll go in water and in water we will be able to carry, it will appear to you a lot lighter because buoyancy force will help you in lifting that object. So you will have only apparent weight to carry, not the actual weight. Okay, so this is the concept of apparent weight, weight of object minus buoyancy force. So if suppose I show you there is a container. Okay, now in this container, this is the liquid, right? And we make one container in that. This is container. and it's going down. This is the container. Okay, and it's going down with certain acceleration because weight is more. Okay, so what you'll write? What will be the acceleration? The acceleration we can write mg minus buoyancy force equal to m into a. Is it that only the apparent weight? Yes. Okay. So mg means what? Volume into density into g minus volume into density into g equal to volume into density into acceleration. Density of this is d. Density of this is rho. Okay. So what we can do here, v and g we can take common. D minus rho equal to Vd into A. What we can cancel? V is cancelled. Now D you bring down. G. D minus rho by D equal to acceleration. So what is acceleration? G into 1 minus rho by D. Acceleration is G into 1 minus rho by D. This is the acceleration of sinking object. Okay. This is the acceleration of sinking object. Okay, fine. Now what? What more we can do? Now we are going to see Stokes' law. We are going to talk about Stokes' law. Okay, what is Stokes' law? Stokes' law talks about whenever the object is going to move in a liquid, other than buoyancy force, there is one more resistance. There is one friction. Friction force is also there whenever one object moves in a liquid. And that friction, he says, is called viscous force. Okay. Stokes' law talks about what? Viscous force. And he said that this viscous force is actually equal to, just a moment. Yes, students. So Stokes' laws talk about viscous force, and he says viscous force is proportional to velocity with which object is moving and is also proportional to radius of the object. When we say radius means he is talking about spherical objects. Okay, object is spherical. For spherical object. Okay, so Stokes' law we are going to apply on spherical objects. Now, spherical objects can be what? Spherical object can be small drops, okay, very small sphere, okay, any sphere of maybe you can say sphere of iron, sphere of mercury, water drop, anything, bubble, it will act on all. So, viscous force is directly proportional to V, is also directly proportional to R. Okay, and he gave the formula as actually viscous force is equal to 6 pi eta RV. And this RV this I am talking about. What is eta? Eta is coefficient of viscosity. Viscosity. And it depends on nature of liquid. It depends on nature of liquid. Viscosity depends on nature of liquid. Okay, right. All right. Now on this one, viscous force, there are certain questions. What questions we can do? The question can be, suppose this is a sphere of radius r and it is coming down with speed v. Okay. Another sphere is there its radius is 2r and it is coming down with speed 3v. Okay, so find the ratio of viscous force on two drops. Let's say these are drops. Find ratio of viscous force on two drops. Okay, this is the question. What to do? Ratio is asking F1 by F2. So we know that force is proportional to RV. So here RV only I'll write. And there what I'll write? 6 RV. That is it. Yes, over 1 by 6. F1 by F2 equal to 1 by 6. Now can we change it into some other mode also? The same question. Yes, we can change. What we can change? Same question we can change in another way. Suppose this is going down with V. Okay. Then its mass is given m and density is given rho. Okay. And this one is here. It's going with 2V. Okay. Its mass is what? 2m and density rho by 2. Something like this. Now same question is asked, what is the ratio of the viscous force on the two? What to do? Now with mass and density, can we talk about radius? Obviously. We know that density is mass by volume. So rho is equal to m by 4 by 3 pi r cube. I am interested in radius only. So r cube equal to m by 4 by 3 pi rho. Okay, for this one then, for this one, this is rho by 2 equal to 2m by 4 by 3 pi r cube. So r cube equal to what? 4m by 4 by 3 pi rho. We are going to write it over here. Okay, so r into v. First is r into v here. This is r into v. And this is r into 2v. This cancel first. Okay, so what we have? R by 2r. What is r? Check. M by 4 by 3 pi rho to the power 1 by 3. And here, what it is? This 4 and 4 we can cancel, right? 3 will go up. 3m. No, don't cancel it. 4 by 3 pi rho will cancel. That is better. Okay. So don't cancel this one. Let it be like that only. So what will come? 4m by 4 by 3 pi rho to the power 1 by 3. So this and this fully cancelled. M and M cancelled. What we got? 1 by 4 to the power 1 by 3. Okay, that's F1 by F. Correct? This is clear? Now Stokes' law gives us one more thing. Talks about terminal velocity. What is this terminal velocity? Now first thing we have to discuss is Stokes' law is acting on the body which is at rest in the liquid or body which is moving in the liquid or sinking. It is based on the body which is sinking with an acceleration. So if it is sinking with an acceleration, we know that its velocity is increasing. If acceleration is there, velocity has to increase. And if velocity is increasing, it means viscous force is also increasing. We talk about this, and if this is inside in liquid, okay, this is inside liquid and it's sinking. Okay, what are the forces which are acting on this one? We know that there is weight is acting down on this. There is obviously buoyancy force acting. And there is viscous force also. This is viscous force. But still it is accelerating. So mg minus buoyancy force minus viscous force equal to ma. Okay, now as it is going down, is this weight changing? No. Is buoyancy force changing? No, because already it's inside. So volume displaced is equal, density, nothing is changing. So these two are constant. But what about this? This is increasing. Why? Because if acceleration is there, acceleration means velocity is going up. If acceleration is there, that means velocity is increasing. And if velocity is increasing, your viscous force, which is 6 pi eta rv, if velocity increasing, viscous force increasing. So terminal velocity concept is the viscous force becomes such because you are increasing. So as viscous force is increasing, its value is such that this acceleration becomes 0. Okay, because it's what? Mg minus buoyancy force minus viscous force. So viscous force become equal to mg minus buoyancy force. You keep on increasing it, velocity was keep on increasing, viscous force keeps on increasing. At one stage, it becomes equal to mg minus buoyancy force. So acceleration becomes 0. Okay. At one stage, velocity increases to a value for which acceleration becomes 0. Acceleration becomes 0. In that case, what will happen? Velocity is called terminal velocity. This velocity is called terminal velocity. Terminal velocity. And in this case, what will be viscous force for us? Viscous force we write as 6 pi eta r Vt. This Vt is terminal velocity for us. Okay, so they ask us this value. Let's see, we'll find it. So what we have? Mg minus buoyancy force minus viscous force equal to acceleration is 0. Okay, so that means mg minus buoyancy force equal to viscous force. Put the value. What is this? Volume into density of that bubble. Okay, this bubble we will make here only, and this is the bubble here. Its density is d. Okay, and the liquid is here. Liquid's density we'll take as rho. Okay, this density is rho. Okay, fine. So volume into density into g minus volume into density into g. Okay, weight minus buoyancy force equal to 6 pi eta r Vt. Okay, now volume, it's a sphere basically. So volume will be what? 4 by 3 pi r cube. So take it outside. Volume into g. Inside is what? Sorry. Inside is d minus rho equal to 6 pi eta r Vt. So this formula we have to remember. That's why we are doing it. Okay. So this is 4 by 3 pi r cube g d minus rho 6 pi eta r Vt. Pi gets cancelled. This is 2, this is 3. That's all. So 2 by 9 eta, 1 r, and this is r square g d minus rho equal to Vt. This is the formula. Okay, so terminal velocity formula 2 by 9 eta r square g d minus rho. Okay, let's solve one question based on this. Okay, now viscous force is there. We know that it's opposing the motion. When it's opposing the motion means it is very similar to friction force. So the question in this one is, this viscous force is proportional to what? Or not viscous force proportional. We'll say that because of its work done, obviously heat will develop. Correct. So what is the power? Power. How much power is developed by this viscous force? That we ask. Okay. Power produced by viscous force is proportional to. I'm not giving you values, that's why I'm writing proportional to. That's fine. What is it proportional to? Power. Okay. Power means, now in this one we all know that this velocity keeps on changing as the body is going down. So when we are saying power, it has to be instantaneous. Instantaneous power means force into velocity. Force into velocity. Okay. And okay, fine. Force is 6 pi eta RV into V. That means this is 6 pi eta R and V square. Now V is what? If suppose I say power produced by viscous force is proportional to when it reaches terminal velocity, then only we can give exactly. Okay. So I'm changing this question. Power produced by viscous force is proportional to when it achieves terminal velocity. When it achieves terminal velocity. Okay, now it's okay. So terminal velocity is there. Terminal velocity calculated. No? This is terminal velocity. 2 by 9 eta r square gt minus rho. So let's put it. That's equal to Vt. Okay. So 6 pi eta r, then 2 by 9 eta r square g d minus rho square. Now in this one, what are constants? Just take it out because he is asking proportionality. So this is out, this is out, this is out, this out, g is out, d minus rho is out. So that means it's proportional to what? R into r square square. That means r to the power 5. So power produced by your viscous force is proportional to r to the power 5. Okay, students. So today we are finishing here. Little bit is left. Okay. We'll see that tomorrow and we will start new topic tomorrow. Right, students? Bye bye then.